Okay, let's start. Do you have any questions? Okay, so first I just want to say for the MATLAB assignment for this week, when you plot the direction field, you will see that there's some straight line solutions that is coded in there. Okay, you can ignore them. The reason is this MATLAB 5. Yeah, exactly, Daniel. That's what I'm trying to say. Like, just comment them out, okay? So that's it. Comment them out, delete them, okay? If you need to, because they're not part of the assignment of this week. They were a part of the week 4 assignment, okay? So that's what I want to say. Any other question? Sharp percentage, something like that. You can Google it. Yeah. All right. All good? Okay. So now I want to round out the discussion on the sketch, okay? Sketch of solutions for 2x2 system. And we have two cases left, right? We have the repeated eigenvalues. And then, of course, here, well, okay, I'll discuss them all. And the second case is, you know, zero eigenvalue, okay? This is a special case. So for the first one, okay, if you have repeated eigenvalue, and suppose, right, this is a 2x2 system. So let's talk about a case when you have only one eigenvector. Then first of all, right, pay attention to the structure of the solution. The solution will be something like this: C1, V1, right, e to lambda t, plus C2, V2, t e to lambda t. Okay, where lambda is our eigenvalue, and lambda can be positive or negative, and V2, right, is our eigenvector. Right? Okay. So again, right, the point of this, the concept of the sketch, right, or the point that we rely the most on the sketch is actually, okay, first of all, right, we should talk about classification, right, of you know, 0, 0, right? Here, 0, 0 is also the only, okay, the only equilibrium solution in this assumption, if we assume that lambda is not equal to 0, right? Because you have repeated eigenvalue, but the eigenvalues are non-zero, so our matrix is still invertible. The matrix y prime, right, equals to ay. So A is still invertible here because the two eigenvalues of A, right, the two lambdas are still non-zero. So we only have 0, 0, right, as the only equilibrium. And so in this case, right, is exactly what you expect. Lambda negative, then it's a sink. Lambda positive, then it's a source. Right? Same as the case where you have distinct eigenvalues. Because also, right, notice that the solutions mostly, right, or your solutions are composed of the two straight line solutions as well, right? Your solutions are composed of the two, wait, hold on. I still fall into a trap with C1, C2, sorry. There's no C1, C2, right? It's just this. V2 eigenvector and V1 the pseudo eigenvector, right? There's no C1, C2. Okay. So in this case, right, actually, so the straight line solution is this one. Okay. But the V1, right, the V1 may not be a straight line because remember, a pseudo eigenvector, right, a multiple of it doesn't have to be a pseudo eigenvector to begin with. So the V1 here is whatever that is, right? In this case, it is exactly a space, a one-dimensional space. But when we want to sketch, okay, so basically our solution is a combination of these two. What we want to sketch, right, or what we rely on is the asymptotic. We rely on the asymptotic. Okay, as t goes to infinity, if lambda is negative, or if t goes to minus infinity, if lambda is positive. Okay. And so, pick one case, for example. Let's say if lambda is negative, then as t goes to infinity, all right, then both of these goes to zero, right? The solution goes to 0, 0. So that's why it's a sink, right? That's why 0, 0 is a sink when the eigenvalue is negative. On the other hand, right, how does it go to 0? In other words, in which direction? In which asymptotic direction? Right, is the question we want to ask, just like the case with the distinct eigenvalues. And here, right, it's kind of clear. And actually, it's kind of, I don't know, good luck that the t term falls on the eigenvector. Because, right, the eigenvector is a straight line solution, while, right, this is not a straight line solution. So here, right, because it's a t here, as t goes to infinity, even though both of these terms go to 0, right, the contribution of the t here makes this term dominating. The contribution of t makes this term dominating. So in other words, the asymptotic direction will be in the direction of the eigenvector. Is that okay? So in other words, right, let's say you sketch this. Okay. And let's say, suppose this is your V2. So this is Y1, Y2, right? This is your V2. So here, right, you could draw a V1 out if you want. But I think, all right, in my opinion, I think the textbook does draw the V1 out. But in my opinion, drawing the V1 out is not useful. And it may be misleading. Because again, right, a multiple of V1 doesn't have to be a solution because V1 is a pseudo eigenvector. All right. In other words, you can draw a V1 out, but another pseudo eigenvector will be a combination of these two to begin with. Okay. So in other words, drawing a V1 is not helpful in this case. And also, right, the asymptotic is in the direction of V2 anyway. So in other words, right, here the lambda is negative, is a sink. Everything goes in like this. Okay, any question on this? So, right, the case with the repeated eigen value, right, with one eigenvector is that the eigenvector becomes the direction of asymptotic. That's it, right? You ignore the pseudo eigenvector. And it's not really no saga. Any question on this? Yes, it's a sink, right, Lauren? You can see that because here, lambda is negative, and the structure of the solution, right, because of this, both of the solutions, right, both of these components goes to 0 as t goes to infinity. Okay, so it converges to 0 as a sink. And the case when lambda is positive, right, is just the opposite. So, right, is 0, 0 is a source. And here, right, the asymptotic is where we look at t goes to minus infinity. Okay, so we kind of ask the question, where does the graph start? Right. But of course, right, there's no starting point exactly because, you know, that's minus infinity, but we kind of pretend, right? By where, I mean, in what direction, not where, right? It starts from 0, but in what direction, right? In what direction? Okay. And again, right, look at this. So this is still the structure of the solution. You're pushing t to minus infinity. So both of these terms go to 0. But again, right, look what term is dominating. The dominating term is still this guy because, right, it has a t, and t is getting large, right? T getting large in a negative direction, but it's still getting large. So therefore, even though both of these go to 0, right, the dominating term is still this. So, you know, in other words, the direction where you're starting from is still the eigenvector v2. Because, right, because again, t e to lambda t is also dominating in this case. Okay, so if you were to draw a picture, right, it will be similar to that one, but maybe let me switch to a different v2, right? Let's suppose this is v2. Okay, this is y1, y2, right? So you come out from this, right, is a source. Like that. Okay. But so the message, right, with the one eigenvector case for a 2 by 2 is that's the only direction that matters, right? The pseudo eigenvector is not a direction to begin with, and it's non-dominating because it's a term without a t. Any question here? All right. So you won't see this so much, right? But let me ask you a question. What if lambda is repeating and we have two eigenvectors? What can we say about the graph? Or can we say something about the graph? So in other words, right, this is a 2 by 2, right? Y prime equals to AY, right? It's 2 by 2. So you got lambda 1 equals to lambda 2 equals to lambda. But in this case, you have both eigenvectors. How would the graph here look? I'll tell you the easy part. If lambda positive, 0, 0 is a source, lambda is negative, 0, 0 is a sink. All right. But so here I assume, of course, lambda is non-zero. But then, of course, right, the question is, what's the direction of asymptotic, right? How do I sketch the graph? Is it V1? Is it V2? What is it? Well, to answer this question, right, you want to, first of all, again, think of the structure of the solution. What does the solution here look like? Y of t will be V1 e to lambda t plus V2 e to lambda t. Okay. So how does the how do you analyze the asymptotic in this case when t goes to infinity, for example, or t goes to minus infinity? So the answer here is, right, that actually it's a trick question. There is no dominating direction, no asymptotic direction. There's no dominating terms. Okay, because the reason is actually here you can just combine these two into one single case like this. And V1, right, is what we mean by this is an abbreviation for any eigenvector. This is also any eigenvector, right? Any direction of this V1, any direction of this V2. So when you combine them like this, basically you get any vector in the plane. So this capture every vector in the plane. So as t goes to infinity, you can get any direction, right, that you come from. And so there's no asymptotic in this case, if you somehow land on this particular context, okay? But actually, it's not that strange, because when is it that you will land on such a problem? Well, you will only see this case, right, as far as I know, happens, right? For example, when you have this case, y prime equals to, let's say, 2, 0, 0, 2, y. Okay? But you see then, if you try to solve this out, basically, this y1 and y2 are kind of, if you solve this out, you'll see that, right? This is just two separate single first order equation. So you got y1, right, is equal to c1 e to 2t, y2 equal to c2 e to 2t, and c1, c2 being arbitrary. That will be 3.5, right, repeated eigenvalue. Sketching. .5, yeah. Okay. So here, right, you see if you plug y1, y2 together, you see you get every single direction. Okay, but of course it's very trivial, right? So you don't have to even think about this. But most of the time you will see this case right here with one single eigenvector. And that's the kind of the genuine case where we have repeated eigenvalue. That's worth talking about. Questions? Okay. So the last thing to talk about is lambda equal to 0. Okay. When you have a 0 eigenvector. So first of all, right, let's talk about this. When y prime equals to ay and lambda equal to 0 is one eigenvector. Sorry, one eigenvalue. Okay. So what do I want to say here? First of all, right, question. How many equilibrium solutions do we have in this case? So I'm referring to, right, like before, when we look at y prime equals to ay, we always say that 0, 0 is the only equilibrium solution. And so we just talk about, right, asymptotic with respect to 0, 0. But now in this case, when you have 1, 0 eigenvalue, right, which I don't think you have seen before, how many equilibrium solutions do we have? No, not just one. Okay, let's take a look at an example. Y prime equals to 1, 1, 1, 1, y. Okay, so what are the eigenvalues? So the eigenvalues is lambda minus 1, right, square, and then minus 1 is equal to 0, right? So you got that lambda minus 1 is equal to plus minus 1. So lambda is equal to 0 or lambda is equal to 2. Okay. So when lambda is equal to 0, right? So here, right, lambda equal to 0 is an eigenvalue. When lambda is equal to 0, right, then you got V1, right, is equal to, let's say, C1 times minus 1, 1. And when lambda equals to 2, right, then you got the matrix is minus 1, 1, 1, minus 1. So V2 is C2, 1, 1. So what is the solution? The solution is C1 minus 1, 1. E to 0t, right, is just 1, plus C2, 1, 1, e to 2t. Notice anything different about the structure of this solution versus the usual one that you look at. Also, notice anything in particular about this matrix. Yep, it's dependent, or this matrix is not invertible. Right? So when what is an equilibrium solution? The equilibrium solution, right, are the ones that solve for ay is equal to 0. And so, for example, here, how many solutions do we have for ay equal to 0? Well, the answer is right here. This one, infinitely many. Okay. So in this case, when you have lambda equal to 0, you will have infinitely many equilibrium solutions. Okay, for the system. Basically, anything along the line of the eigenvectors of that corresponds to lambda equal to 0 is an equilibrium solution. Okay, so for example, right, you see this changes the whole thing here, right? Because lambda equals to 2 is positive. For asymptotic, we want to look at t goes to infinity, t goes to minus infinity, right? But when t goes to minus infinity, for this particular y, what is the limit? Is it 0, 0? Well, it's not, right? It's going to be this one. Okay. So in other words, suppose you were to sketch the graph of this. How does it look? So first of all, right, there's the direction minus 1, 1. But on this direction, be very careful. There's no movement on this direction, okay? Basically, if you start anywhere here, you stay there. So this line is the whole line of the equilibrium solution, okay? And then this limit tells you that any other solution, right, starts from here, starts from some point here, and go out. So you have, so the 1, 1 is this direction, right? So you have basically solutions that go out from here. Like this. Is that okay? So that's the nature of the solution or the sketch of the solution when you have 1 lambda equal to 0. It's not a curve, okay? It's not going to be a curve. It's going to be something like this. And by the way, right, so here, basically what we're trying to say is from minus infinity, it starts to go out in either direction. That's what we're trying to express, right? So it doesn't really touch that line. But question? So the case we just described above, right, is the case when we have 1 lambda, so above, right, is when we have 1 lambda equal to 0, and the other one is, what do I want to say, this lambda positive, right? The lambda 1 equal to 0, and lambda 2 is positive, okay? And then, so for the case when lambda 1 is equal to 0 and lambda 2 is negative, all right, then you have a very similar graph, right? But the direction will be going in, okay? So let's say that V1, right, wherever your V1 is, suppose this is your V1. All right, and this is your V2. Then you will be static on V1. You don't move on V1 because V1, right, is the eigenvector corresponding to lambda equal to 0. And you will move, right, toward V1, right, because lambda 2 is negative. You will move toward V1 along the direction of V2. So when I draw this arrow, I just indicate the V2, but you would move like this. Okay. Question. All right. So for the last one, related to this, is it possible to have two eigenvalues being 0 in a 2x2 matrix? So here, right, I described the case when one of the eigenvalue, right, is 0 and one of the eigenvalues is non-zero. Okay. Is it possible to have two eigenvalues being 0 in the 2x2 case? Well, yes, it's not a no, but what would the matrix be in that case? Correct, right? So we don't discuss that exactly. It's a 0 matrix, or like it's almost right, because you could have this case like 0, 0, 0, 1 or something like that. Okay, so this will also have two eigen values equal to 0. So here, right, basically you got two solutions to be constant, so there's nothing to do there to begin with. Okay, you got two constant solutions. Nothing to sketch. Okay. So again, I mean, what we discussed so far round off, right? All possible sketching for all different cases, eigenvalues, eigenvectors. But of course, right, this is only for 2x2, and it generalizes to high dimension, all right? But the key concept, right, for complex eigenvalue, for repeated eigenvalue, for 0 eigenvalue, okay, can be repeated, all right, into the high dimensional case. And I want to emphasize again that for lambda equal to 0, the key concept or the key thing you want to remember is that you have infinitely many equilibrium solutions, okay? And in a 2x2, a consequence of that is that we don't have the curve solution. We have straight line solutions. So here, right? Oh, hold on. No, you're right. I shouldn't say. Let me see, hold on. So for example, let's take a look at this. Is it two constant solutions or one of them is t? Let me see. So let's say y prime, right, is equal to 0, 0, 1, 0, y. Okay, so what does this mean? So that means that y1, right, is c. Okay, and you got y2 prime is equal to c1. So I think you're right. Y2 prime is c1t plus c2. You're right. So, interesting. So it's not two constant solution. Thank you. I was wrong there. That's not two constant solutions. I was thinking of the case when the matrix A is purely the 0 matrix, then that's true. In this example I give, it's not true, right? One of the solution is like this. But either way, I guess my point is that here, there's still nothing to sketch because what do I want to say here, right? The sketch of the graph here is, what do I want to say? So I still want to say that here, right? That in this example, okay. You know, the sketching is still trivial. How about that? Okay. So yeah, thank you for pointing that out. That is not true in this example that I give. All right. But I mean, like, I guess when you have these kind of solutions, right, no one's going to be super interested in how the solution look like because you can just really do them one by one. All right. Any other question? All right. So for the next material, I want to talk about the supplemental N4. Okay. In the math department website is the matrix exponential concept. Okay. So this is not in the book. This is on the math department website. Okay. And here, right, the point of this discussion is this, that suppose we consider, okay, suppose look at the one-dimensional first order ODE y prime equals to ay. Okay. Then the solution here is y of t is c e to at. All right. So now suppose that we have an n-dimensional linear first order ODE where you have y prime equals to ay. What we want to say is the solution y of t is y of 0 e to at, where oh, sorry, here is y0 on this side, where e to at is an n by n matrix. Okay. So the discussion here is how to understand this term e to at, where a is a matrix. And the goal, right, is to unify the solution of the system y prime equals to ay under one single expression like this, rather than, you know, dividing into cases with eigenvalue, eigenvectors. Okay. There's pros and cons for these two approaches. The approach here is very mathematical and it has its advantage of conceptually being very, very appealing, and is very similar to the one-dimensional case. But the drawback, of course, is in practical use, we don't necessarily, okay, compute things this way. But first, I want to discuss what this is all about and do some examples, and then draw the conclusions, draw the comparisons with the techniques that we have talked about so far. So first, right, the definition of e to at. Okay. So given, or maybe let me do this, e to the a. Given a matrix A n by n, how do we define, right, the matrix or e to a? Okay. And for that, we draw the inspiration from the one-dimensional case. So in the one-dimensional case, in the scalar case, if a is a number, okay, given a number a, then e to the a is defined. There are many ways to define it, but one way that's very useful for us is an infinite sum. Okay. And one thing you want to remember is that this sum converges for all values of a. Okay. So that means that this function, right, as if we define it as a power series, is well defined for all values of a. So using or being inspired by this, when A is a matrix, when A is a matrix, okay, we define e to the a to be same way, the matrix A is raised to the n over n factorial, n from 1 to infinity. All right. So it's important for you to, first of all, kind of try to see what's going on in this formula. So A as an n by n matrix, then A to the n, right, A raised to n power. Let me change it to another power because I use n as a dimension. Let me do k, okay? So A to the k, right, is a n by n matrix. So what happens, right, and divide by k factorial is dividing by a scalar. So what happens here is you sum up all, like, an infinitely many numbers of n by n matrices. And when you add them up and suppose that converge, then you define that final matrix, which is also n by n dimension, as e to the a. All right. With, of course, the caveat, right, that a to the 0 by definition is the identity. Okay. Questions so far? Well, let's take a look at one example. Suppose that A is a diagonal matrix. Let's say, well, let's take the easiest one, 1, 0, 0, 1, the identity. Okay. What would e to the a be? Well, let's follow the formula, right? E to a is the sum starting from 0 to infinity of a to the n, sorry, a to the k over k factorial. And that would be, right, for this matter, because a is the identity, let's plug that in. And the identity raised to any power is the identity. So we just have this. Okay. So let's try to imagine what's going on with this sum. So what we have, right, is this. You first have 1, 0, 0, 1. This is a term when k is equal to 0. Next, you have the term 1 over 2, right, factorial. Then you have 1 over 3 factorial. Right, this is exactly k. Sorry, I missed one. K 1 factorial. I missed that. So let me change this. So I think this is not, the harmonic series refers to the sum of 1 over n. Okay, so this is not harmonic series, but it's a power series of e to the x in matrix form. Right here. It comes from exactly this, right? Yes, the point is actually it converges for any matrix, which is a little harder to see. But here in this case, it's very easy because it breaks down to just individual components. Yep. But the fact is that it converges for any matrix possible, not just this, okay? Saga, I suppose you correct me on this. And yeah, thank you, right? 0, 1, 2. So the point is, right, you see that this sum together just gives us sum over 1 over k factorial, 0, 0, sum over 1 over k factorial, k from 0 to infinity, which gives us e 0, 0, e. And let me put e to 1 here, just for emphasis. Okay, so we have shown, or we have checked that e to the I is e to 1, 0, 0, e to 1 for 2 by 2. And of course, you know, n by n is the same. And let me do this, right? Plus dot, dot, dot. It's not just that. Any question here? Yeah, e to the 1, or just e, right? I emphasize e to 1 because you see why. The 1 here corresponds to the 1, 1 of the identity. Starts at 0, starts at 0. Because basically, right, e will be this. So e to the sum of e to the k over k factorial, k from 0 to infinity. Start at 0. I mean, it'll be more familiar to you like this. E to the x, right, is 1 plus x squared over 2 plus x cubed over 3 factorial, right? So you see, that's why it's confusing, because when you do e to the 1, you pick up two 1 terms. But it really starts at 0. It doesn't start at 1. 1 is the first power. Any other question? Okay. So now let's explore when A is a diagonal matrix, let's say 3, 0, 0, 2. What would E to A be? Well, so again, right, let's follow the formula. What we have, right, E to A is going to be the sum k from 0 to infinity of A to the n over, sorry, A to the k over k factorial, right, which starts out with the identity, right, and then A to the first power, and then A to the second power, and then to the third power. Right? Okay. So what do you get when you raise a diagonal matrix to a power? What you get, right, is exactly the diagonal matrix, but with the power affecting the diagonal terms. Okay. And so you see, right, that exactly that the term just sum up along the diagonals, giving you sorry, sum of 3 to the k over k factorial, k from 0 to infinity, sum of 2 to the k over k factorial, or this is just e cubed e squared. Question? So basically, right, the conclusion here is that if A is a diagonal matrix, then e to the A is the exponential of the diagonals. Okay. All right. So what about general matrices? Okay. What about general matrices? So for general matrices, what we want is we want to somehow simplify this expression. we want to somehow simplify this expression, because if you raise a matrix to the kth power, that's not fun. All right, if you raise a matrix to a 10th power, where the entries, right, where it's not the diagonal matrix, that's not a trivial task. So in general, okay, a to the k is time consuming to compute. But, okay, if A is diagonalizable, that is, if A is PDP inverse, where P is an invertible matrix, and D is diagonal, then A to the K is PD to the K P inverse, where D to the K is easy to compute because you just raise the individual entries of the diagonals to the kth power. In other words, if D, right, let's say is lambda 1, 0, 0, lambda 2, we have discussed that, right, D to a K is just lambda 1 raised to a K, 0, 0, lambda 2 to a K. Okay. So the point is that to compute the exponential of a matrix, you necessarily want to compute a power, its power, up to any arbitrary power. But that's hard in general. Okay. On the other hand, though, if you have a diagonalizable structure, then raising it to any power is easy because the power, the job of the power, only falls under the diagonal term, the diagonal matrix. Okay. Do you see why this is true? The reason, right, is because the P and P inverse just cancel each other out when you multiply them together. For example, when you do A squared, right, that means is P D P inverse times P D P inverse. And matrix multiplication is not commutative, but is associative. So you can combine these two. P inverse P is identity, so you got is exactly P D squared P inverse. And once you have this, then you're on a roll. Because, for example, next is A cubed. A cubed is exactly A squared times A. Well, what's A squared? We just got A squared is P D squared P inverse. And then A is P D P inverse. Again, these two guys group up to cancel, giving you P D cubed P inverse, so on and so forth. Okay. So in other words, if A is diagonalizable, then, okay, e to the A, okay, will be the sum of A to the K over K factorial, K from 0 to infinity. If it's diagonalizable, then we can write A as P D P inverse raised to K power. But then by what we just say above, you got the k power inside. And matrix multiplication, right, follows the same factorization rule as anything else. So you can factor the P and P inverse out to give you this. P, the sum of d to the k over k factorial times P inverse. Okay, so from here to here, we factor the P and P inverse out. But so what do we have? What we have is, you see, that we transfer the case when A is diagonalizable back to the case where we just add the diagonal matrices. And this, right, you recognize is just e to d. And so the case when you can compute e to the a most easily is when the matrix is diagonalizable. Because if it's diagonalizable, then e to the a is exactly this. Now, that's not to say that it's not computationally time consuming, but it's much, much, much better than having to raise a to a power, okay? To raise a matrix to an arbitrary power. You will never be able to accomplish this in closed form, in closed computation. But here, right, this is in closed computation, at least if you know how to do e to some numbers. Question? Okay. So 0. What are you trying to say, Daniel? Oh, you're answering to Carl? Yeah. Okay. So, all right. Yeah, he asked that a long time ago. So the next question obviously is this, right? How to find P and D, all right? Question: when is A diagonalizable? Okay. And then, if so, how to find P and D? So the answer here is actually very, very simple. The answer is when A has a full set of eigenvectors, in that case, D is the matrix formed by the eigenvalues and P is the matrix formed by the eigenvectors. The catch, right, is that you must line things up correctly. In other words, if you write lambda 1 and then lambda 2, then you must write v1 first before v2. Okay? And so that's the answer for the diagonalization. All right. Now, any question here? So now, okay, now, correct, full set. Yeah, so exactly, even when eigenvalues are repeated, as long as you have full set, you're good. So now, right, some of these are quite abstract, but that's the nature of this discussion, okay? Again, remember, the goal here is to somehow put a unifying approach, right, to the solution via this structure. This is the one and only goal, all right? call it impractical if you want, but it is practical in some discussion, all right? But here, of course, the goal is not to give you the easiest way to calculate the solution, but it gives a unifying approach to discuss how to solve, right, a matrix system, okay? And so, because notice that the approach here does not care whether A has repeated eigenvalue, complex eigenvalue, distinct eigenvalues. It never says that, okay? The discussion down here that I was talking about was more of already catering to the computational approach, because I say that if A is diagonalizable, then you can calculate it. But the abstract structure doesn't even care about that, okay? It just says that that's a solution. But anyway, so to bring some of these discussions a little bit more down to earth, I will look at the exam question, all right, question 1, and demonstrate to you how we would solve this using the exponential approach. So the exam 1, right, you have A equals to 4, 2, 1, 3, okay? And you got lambda equals to 2 and 5. You got V1, right, corresponding to lambda equals to 2, to be 1 minus 1, and lambda equals to 5. V2 would be 2 and 1. Okay, I think this everyone would get. Now I know that here you would just write down the solution, right? I would do the hard way, the painful way, okay, the exponential way. But just to demonstrate to you that we get the same solution at the end of the day. And so what would the exponential approach do? The exponential approach would form the D matrix, which is 2, 0, 0, 5. And the P matrix would be 1, minus 1, 2, and 1. Okay? The proposed solution will be y of t to be e to the at times y0, where y0, right, here would be e to at times 1, 0, because that's the initial condition that I proposed, that I give, okay? So we will calculate this and then show that, right, it is equal to the solution that is given from, or you know, that's how you would get from the eigenvalue eigenvector approach. So what's e to at, right? So first, let's just look at e to the a, okay? So e to the a, e to at, I guess, is e to the p d. Let's put a t here, right? P inverse. T is a scalar, right? T is a scalar, so I can put it anywhere I want. So I would associate that with the diagonal part, because then, right, it will be p e to the dt p inverse, okay? Which would be right here, 1 minus 1, 2, 1, e to a 2t, 0, 0, e to a 5t, all right? Now P inverse is what, right? Let me calculate P inverse out. P inverse is, let's see here. So 1 minus 2, right, is 3, so 1/3. Switch this, negate that. Okay, that's P inverse. So you would multiply this with 1/3, 1 minus 2, 1, 1, and finally with 1, 0. Now I claim that if you calculate all this out and when all the dust settle, you'll get exactly the solution you get from part B of the exam. Okay. Oh, sorry. Is it part B? Part B. Yeah, part B. Okay. So let's see, right? So you can just multiply from right to left, I think. Yeah, absolutely. And all these structures are quite consistent with each other, all right? But I'm here, I'm describing it just to show you that, right, you get the same thing anyway, albeit like a more painful approach. But the value here is not, right? I'm not claiming that I'm doing a faster way. It's, as you see, I'm wasting time here, right? But on the other hand, the value is I can put all the structure together in one single answer, and that's very helpful mathematically. Okay, but here I'm just demonstrating for those of you who don't see, right, the concrete examples that yeah, we're doing the same thing. Okay, but anyway, let's calculate, right? So I multiply from right to left. All right. So from right to left, I get 1 minus 1, 2, 1, eta 2t, 0, 0, eta 5t. And then here I got 1/3, 1/3, right? And then right to left, 1/3, eta 2t, and then 1/3, eta 5t. So finally, I should get, right, 1/3, eta 2t plus 2/3, eta 5t minus 1/3, eta 2t plus 1/3, eta 5t. Is that what you got? I mean, you can check your answer, see if you got 1B right. But that's the 1B solution. Any question here? Summation approach? What do you mean by that? Yeah, I mean, you know how to do that already, right? And so whatever you did on the exam should get you the same solution as this. Okay. So now what else do I want to say here? So yeah. Now I'll just do this, right? For the brave, try this on number 2 of the exam. Okay. If you really, have nothing better to do tonight and you want some entertainment. The reason is, right, if you remember, 2 has complex eigenvalues. Correct. The beauty of this approach is it works. It works perfectly, right, for any kind. And a complex matrix is still diagonalizable, exactly the same D and P structure as we did before. But the point, right, the reason why I say the brave is not that bad, but you will have to take inverse and do computation with imaginary numbers, right, complex numbers, and that will be a little bit more painful than this example. So I'm not gonna, sit here and do it for you. But if you try it, you will get the same answer as you get for 2B using this approach as the one, that we did on the exam. Okay. So again, right, just trying to say that all these approaches are consistent. Okay. Now, so tying up some loose end, okay? Meaning I want to explain, right, that why this works and that kind of thing. So first of all, right, again, the key message is that if you have the matrix system y prime equals to ay, okay? The issue is, of course, a must be constant, right? I'm not talking about a having, uh, variable entries here, like a depends on t, that kind of stuff. This doesn't work. If a is a constant matrix, then your solution will be e to a t y0, okay? Any a. So the value is simple answer for any system, any homogeneous system. Of course, the drawback or the disadvantage is no explicit solution. In other words, right, I mean, people would not appreciate it when you write this down for them, because what does it mean, right? What are the numbers? What are the values, right? But if you understand the content behind this, right, you understand the mathematical content behind this, and it's not really an empty answer. It's just not explicit, okay? And second, even if, right, even in the case of explicit solution, even if explicit solution is possible, in other words, right, A is diagonalizable, the computation is impractical. Is not efficient. Let me put it this way. I mean, roughly speaking, right, you still have to compute the eigenvalues, eigenvectors anyway, right? So this approach is not that bad compared to the other approach, except that notice that in this approach, you have to calculate P inverse. And calculating an inverse, right, just add one extra layer to, your computation. But you know what, right? This inverse right here exactly corresponds to the step when you have to solve for the initial condition, right? If you were to use the traditional approach, the eigenvalue eigenvector approach, then you have to solve for C1, C2. So you have to solve a system. So here, if you notice, this inverse right here is a sneaky way to calculate the C1, C2 for you directly, right? Here, this form right here requires no solving the system, okay? It's just straight out, that's the solution, okay? But of course, there are more efficient way to solve a system than taking an inverse. So that's why the computation is not efficient from that point of view, okay? But of course, again, the simple answer is worth the price in the abstract discussion. Now, the second point I want to say is, right, also pay attention. I'm very mindful to write this, right? Notice at the beginning I was writing this, and I erase it immediately. The reason is you're in vector context here, all right? The order of multiplication matters. This is a matrix and this is a vector, right? If you put a column vector in front, they don't multiply, right? If you put the vector in front like this, there better be a row. But I think even in a row, I think that's not the what you meant, okay? That's wrong. So the order matters. And so finally, right, I just want to discuss real quick on why this works. So meaning, why does this solution work? Okay. So the reason is actually very simple. If we define e to at, right, consistently, which we did, then if you differentiate e to at, guess what you will have? You will get hold on, you get e to at times a, which is, so roughly speaking, you should get this. But it's also equal to this. Okay. So I think time's up. So we'll continue next time to finish this. But here is a chain rule for matrix form. And here is the reason is because e to at and any power of a commute. Okay. And exactly because of this, right, you see that when you differentiate both sides and you bring the a down, you got exactly y prime equals to ay. Okay. And that's the reason. So next time we'll finish this and then we'll conclude this exponential matrix approach. It's a very abstract approach. It's not practical, but it's something you should keep in the back of your mind if you do some, more advanced math where you don't care to write down the explicit solution, but you just want to have a structure of the solution in front of you to discuss about, certain things. Okay. All right. So if you have any question, I'll answer. If not, I'll see you on Thursday. Yeah. Thank you. Thank you. You too. Thank you.